Hello students! Today we are going to finish our chapter on molecular structure in Module 6. Please go to page 10 of your notes. So the concept of hybridization relates the geometry of the molecule to the orbitals that are involved in bonding or containing electron pairs. This table relates the geometry around an atom to its hybridization state. A linear framework corresponds to an sp hybridization. A trigonal planar framework, whether it's AB3 or AB2E, corresponds to an sp2 hybridization of the element. A tetrahedral framework, whether it's AB4, AB3E, or AB2E2, corresponds to an sp3 hybridization. A trigonal bipyramidal framework, whether it's AB5, AB4E, AB3E2, or AB2E3, is an sp3d hybridization, and an octahedral framework, whether it's AB6, AB5E, AB4E2, is an sp3d2 framework. Over the next few slides, we are going to explain this concept of hybridization using carbon as an example. So when we talk about methane, we realized that it was a tetrahedral molecule, an AB4 system with 4 equivalent CH bonds. However, when you think about carbon from the periodic table, its ground state configuration is 2s2, 2p2. How do these 2s and 2p orbitals of very different shape and orientation make up for 4 equivalent covalent bonds? In fact, upon forming 4 bonds, carbon always takes an excited state. One of the electrons in the 2s orbital is promoted to the 2p orbital. This way we have 2 half-full orbitals that can form 4 bonds. When making 4 single bonds, the 2s and the 3 2p orbitals mix with each other or hybridize to give 4 equivalent hybrid orbitals that we call sp3 hybrid orbital. Why sp3? Simply because they're made of 1s and 3p orbitals. So think spp gives sp3. These orbitals point to the 4 points of a tetrahedron. The small lobe points inwards and the big lobe points outwards. They have 25% S character and 75% P character. Again, remember SPPP. So in methane, each of these sp3 hybrid orbital overlaps with the 1s orbital of the hydrogen atom to give what we call a sigma bond. It's a front-end collision of 2 orbitals. So overall, carbon in methane has 4 single sigma bonds, and it is sp3 hybridized and tetrahedral. Looking at ethylene, it is a planar molecule. Both carbons have the geometry AB3 trigonal planar. In this case, the geometry is defined by 3 hybrid orbitals made of the 2s orbital mixing with only 2 of the 2p orbitals, giving 3 sp2 hybrid orbitals. These orbitals have 33% s character and 67% p character. They have a large lobe and a small lobe, and a large lobe are pointing to the point of a triangle. We have one non-hybridized p orbital that is perpendicular to the triangle defined by the sp2 hybrid orbital. So when we look at the bonding in ethylene, each of the sp2 hybrid orbital is going to be forming a sigma bond. 2 sigma bonds with the hydrogens overlapping with the 1s orbital. And the third sigma bond is formed from the overlap of the sp2 orbital of one carbon with the sp2 orbital of another carbon, of the other carbon. We have 2 orbitals that are now not hybridized, one on each of the carbons. These 2 orbitals are going to be overlapping sideways to give us what we call a pi bond. So the pi bond has one lobe above, one lobe below, and it's the side overlap of non-hybridized p orbitals from each of the carbon in ethylene. So overall, looking at ethylene, both carbons are sp2 hybridized. Each carbon forms 3 sigma bonds with the sp2 hybrid orbitals and 1 pi bond with the non-hybridized p orbital. The geometry is trigonal planar. This will always be the case when a carbon forms 2 single bonds and 1 double bond. So a double bond is made of a sigma bond formed by the head-on overlap of hybridized atomic orbitals, and a pi bond is formed by the side overlap of non-hybridized p orbitals. So let's talk about acetylene now. It's a linear molecule. Both carbons are AB2. In this case, we will have 2 sigma bonds defining the geometry and 2 pi bonds. We have the 2s orbital and 1 2p orbital that are combining to give 2 sp orbitals, which are 50% s and 50% p, and are arranged linearly. Thus, we are left with 2 non-hybridized p orbitals perpendicular to one another. You can see them here in green and yellow. Each carbon forms 2 sigma bonds, one with the 1s orbital of a hydrogen and one with the other sp orbital from the other carbon, and 2 pi bonds by the side overlap of the non-hybridized p orbital. So to summarize, the 2 carbons in acetylene are sp hybridized. Each carbon forms 2 sigma bonds and 2 pi bonds. This will always be the case for carbon when it makes a triple bond. It is linear sp hybridized, forming 2 sigma bond and 2 pi bond. Thus, a triple bond is made of a sigma bond formed from the overlap of hybrid orbitals and 2 pi bonds made from the overlap of non-hybridized p orbitals. So hybridization provides the explanation for the geometry of molecules when atoms, if you remember, individually have atomic orbitals of various shapes. The s, p, and d orbitals mix in the appropriate amounts to give the various shapes deduced from the VSEPR theory. Carbon makes a maximum of 4 bonds, so it can be sp3, sp2, or sp hybridized. If we only have single bonds, the framework is tetrahedral. It is sp3 hybridized. If we have 1 double bond and 2 single bonds, it's trigonal planar and sp2 hybridized. If we have a single bond and a triple bond, it is linear and it is sp hybridized. Note that other elements like oxygen, nitrogen in the second period will also make bonds in hybridized state. Since lone pair are geometry defining, remember ABE for instance, they will be in hybrid orbitals. Elements beyond the third period can form up to 6 bonds involving the orbitals. So a trigonal bipyramidal geometry will involve a total of 5 orbitals, adding 1 d orbital to the s and 3 p orbitals, so the hybridization will be sp3d. An octahedral geometry with 1 more d orbital than above will be using a hybridization state sp3d2. Let's take a couple of examples. Let's look at this organic molecule. We can look at each carbon and define its hybridization. Carbon A has 2 single bonds, 1 double bond. Therefore, it is sp2 hybridized. Carbon B has a double bond and 2 single bonds, 1 to the H and 1 to the other carbon. It's also sp2 hybridized. C has 4 single bonds. It's sp3 hybridized. E has a double bond and 2 single bonds. It's sp2 hybridized. How about the oxygen? Let's look at F. F has 2 lone pairs and a double bond. If you think about it, it's an A, B, E, 2. So it's a trigonal planar system. Okay? It's a geometry that is corresponding to an sp2 hybridized state of the oxygen. The 2 lone pairs are carried by sp2 hybrid orbitals. How about oxygen G? It's an A, B2, E2. It's a tetrahedral framework. It's a bent geometry, but it's a tetrahedral framework, which means that the oxygen here is sp3 hybridized. The 2 lone pairs are carried by sp3 hybrid orbitals. Okay, let's do an example with bromine in BrCl3 and answer the question, what is the hybridization state of the bromine is BrCl3? So for this, we need to first write a correct Lewis structure. And you see that this is an AB3E2 framework. So the framework is trigonal bipyramidal, and the hybridization state of the bromine, 1, 2, 3, 4, 5 element, you need 5 orbitals, s, p3, that's 4, and we need 1d, so it's sp3d. That's the hybridization state of bromine in BrCl3. Okay, this concludes Module 6 on molecular structure. Now go to Activity 6 to practice this concept. Okay? Bye for now.